z-tests, and we also went over, we went over the one sample mean z-test, as well as the one sample mean t-test, and we're going to move on to something called the student to independent samples t-test. So we're now going to be on, let's see, we're on the middle of page 8. So the two independent means t-test, also known as the student t-test. Although the one sample mean t-test that we did yesterday has its uses, it's not the most frequently used t-test. A much more common situation arises when you have two different groups of observations. So, for example, in psychological research, this tends to correspond to when you have two different groups of participants. So this might be where each group corresponds to a different treatment condition within the study. So for example, you may want to compare a treatment group versus a control group, or you may want to compare two different treatments. So for each person in the study, you measure some outcome variable of interest using an interval or a ratio level scale. And so the research question that you're asking is whether or not the two groups have different population means. This is the situation that the independent means t-test is designed for. So then there will be a few assumptions of this independent samples t-test. So as always, our hypothesis test relies on assumptions, just like we talked about yesterday. So what are they? So for this student t-test, there are 3 assumptions, and some are going to be the same that we previously discussed when we were talking about the one sample t-test. So again, there's normality, and so like with the one sample t-test, it is assumed that the data are normally distributed. Specifically, we're going to assume that both groups are normally distributed, and then later on in this chapter, we're also going to see a few ways that we can statistically check for normality, which will be very helpful. That said, because those statistical approaches are heavily impacted by your sample size, at this point we're not going to rely on them too heavily. The second assumption is the same as with the one sample t-test, so independence. Once again, it is assumed that the observations are independently sampled. So in the context of the student test, this has 2 aspects to it. So firstly, we assume that the observations within each sample are independent of one another, exactly the same as for the one sample test. However, we also assume that there are no cross-sample dependencies. So if, for instance, it turns out that you included some participants in both experimental conditions in your study, like for example by accidentally allowing the same person to sign up to different conditions, then there are some cross-sample dependencies that you'd need to account for. The third assumption for the independent samples t-test, or the student t-test, is homogeneity of your variance. So this third assumption is new, and this assumption is that the population standard deviation is the same in both groups in your study. And you can test this assumption using the Levine test. That's L-E-V like Victor, E-N like Nancy, E. So the Levine test. And we're going to also talk about that later. So like the statistical tests for normality, the Levine test is also heavily impacted by sample size. And if there is ever a concern about this homogeneity of your variance, so if there's ever a concern about this particular assumption, which states that the population standard deviation is the same in both groups, you can then conduct the Welch t-test instead of the student t-test. And so the Welch t-test does not assume the homogeneity of variance with your two samples, okay? So again, we will get into the Welch t-test in section 9.4. At this point, we can pull up another data set, which is the Dr. Harpo's class data set. And with this data set, we've already played around with it in another exercise in a different chapter, but let's review what is in this data set. So suppose we have 33 students that are taking Dr. Harpo's statistics class. There are two tutors for this class. There's Anastasia and Bernadette. And so in Anastasia's class, there's 15 students, which is N1. And in the other class, Bernadette's class, where she's the tutor, she has 18 students. So N2 equals 18 for that class. So a research question that we would be interested in for this Dr. Harpo example is if Anastasia, the tutor Anastasia, and the tutor Bernadette, if their students actually have different grades in the statistics course. So Dr. Harpo emails the course grades, and they're in the Harpo CSV file. So we're going to open that up and load the file into JASP, and then we're going to take a look at what variables it contains. So we're going to open it up in a minute, but just to remind us, this data set has 3 variables. So we have the student ID, right? We have the grade, and then we have their tutor assignment, so whether they're assigned to Anastasia or Bernadette. So not surprisingly, the grade variable contains the student's grade. Again, the tutor variable is the factor that indicates who each student's tutor was. And then in a moment, we will upload that. There is a calculation noted here that the means and the standard deviations were already calculated for us. So here's a little summary. So for Anastasia's students, the mean grade for her tutoring section was 74.53 with a standard deviation of 9.00, and again, N for her class was 15, N equals 15. Then for Bernadette's class, where she was the tutor, the mean grade is actually lower. That was calculated at 69.06 with a standard deviation of 5.77, and the N for her number of students was 18. So N2 was 18. And then we're going to load the data, and we're going to plot the histograms like we've been doing, and we're going to show the distribution for each tutor, as well as a simpler plot which will show the means and the corresponding confidence intervals for both groups of students, and we will compare it to what is listed in our section. So let's go ahead and keep going for now, and then we'll do it all at the same time. So again, we're learning about the independent samples t-test here. It's also known as an independent t-test or two independent means t-test. There's quite a few synonyms for this test. And it does come in two different forms, so that is what's really important here. So there is the student independent t-test form, and then there's the Welch's independent t-test. So the original student t-test, which is the one that we're going to describe first, is the simpler of the two, but it does rely on much more restrictive assumptions than the Welch's t-test. So assume for this moment that you want to run a two-sided test, and the goal is to determine whether two independent samples of data are drawn from populations with the same mean, which would be your null hypothesis, or if they are drawn from different means, that would be your alternative hypothesis. So when we say independent samples, again, what we really mean here is that there's no special relationship, right? There's no correlation or association between the observations in your two samples. This might not make a lot of sense yet, but it will be clearer when we come to talk about the paired samples t-test later on. But for now, we're just going to point out that if we have an experimental design where our participants are randomly allocated to one or two groups, and we want to compare the two groups' mean performance, like the test grades, on some outcome measure, then that would be where we use this independent samples t-test rather than the paired samples t-test. So let's move on to page 8. Onto page 10, and we're going to go back and we're going to write our null and our alternative hypothesis. So let's assume that we're going to use mu1 and mu2. So let's let mu1 denote the true population mean for group 1, which will make Anastasia students. And mu2 will be the true population mean for our second group, and that will be Bernadette students. So then our null hypothesis would say that mu1 equals mu2, okay? And then our alternative hypothesis would be that the groups are not equal, okay? The grades are not equal. So mu1 does not equal mu2 would be the alternative hypothesis. And so we're just going to write those out, which are we already see written on page 10. And let's see. Then we're going to, just like in our one sample test, we're going to plug our values into our complicated statistical equation. And this way we can be precise about exactly how close to 0 that our difference might actually be. And the solution to this problem is more or less the same. We will calculate a standard error estimate, or SE, just like we did last time, and then we'll divide the difference between the means by our SE estimate. So we'll just push through this by hand calculation because the software will do it for us. But if we want to see what that calculation actually looks like, we can examine page 10. So let's keep pushing through to page 11. And we're going to look at our pooled estimate of the standard deviation next. So in the original student t-test, we make the assumption that the two groups have the same population standard deviation. So that would mean regardless of whether the population means are the same, we assume that the population standard deviations are identical. And since we're assuming that the two standard deviations are the same, we can drop the subscripts and refer to them both as sigma. So how should we estimate this standard deviation? How should we construct a single estimate of a standard deviation when we now actually have two samples and not just one? So the answer is basically we're going to average them. So we're going to take a weighted average of the variance estimates, which we use as our pooled estimate of the variance. So the weight assigned to each sample is equal to the number of observations in that sample minus 1. So mathematically, we can write it as n1 minus 1 and n2 minus 1. And then we can plug it into our complicated by hand equation. And then we're going to take the square root, and that way we can get our pooled estimate of our standard deviation and our variance. So when we're computing the t-test statistic, we now have our pooled estimate of the standard deviation, and from now on we're going to drop the silly p subscript and just refer to this as the estimated standard deviation. So now we're going to go back to thinking about our hypothesis test. So our whole reason for calculating this pooled estimate was that we knew it would be helpful when calculating our standard error estimate, but the standard error of what? You know, in the one sample t-test, it was the standard error of the sample mean. So we had SE equals standard deviation divided by the square root of our big N. This time though, we have two sample means. So as a consequence, the standard error that we need to divide by is in fact the standard error of that difference between the means. And as long as the two variables really do have the same standard deviation, then our estimate for the standard error is this equation on page 11, and then we get our test statistic. And again, the software is going to do this really lengthy math for us for all of our numbers of variables, and that's why the software was created. But just to remind you, just as we saw with our one sample test yesterday, the sampling distribution of this t statistic is a t distribution. As long as the null hypothesis is true and then all of the assumptions of the t-test are met. The degrees of freedom, however, will be slightly different. As usual, we can think of the degrees of freedom to be equal to the number of data points minus the number of constraints. So in this case, we have n observations, we have n1 in sample 1 and n2 in sample 2, and we have two constraints, which are our sample means. So the total degrees of freedom for this test is actually n minus 2. We're not going to be doing all the hand calculations because we don't have to. In real life, nearly everyone nowadays uses this statistical software, maybe JASP or SPSS or one of many. So we're going to just use JASP, and let's take a look here. So we're going to plug all of our data into JASP, and it's going to calculate our t-test statistic and also the p-value and confidence interval. We're going to move into page 12 and do our example for the Harpo data set. So let me see. We're going to escape here. We're going to pull up JASP. So there's our JASP. And then we're going to go to the little hamburger here. We're going to open up the Harpo file. There it is. Open. And the outcome variable for our test is going to be the grade. So we're going to open up the t-test, and we're going to, yesterday we did the one sample, and now we're going to do the independent samples t-test. So open up this, and we're going to move the student grade into the dependent variables box. Boom. And then we're going to move the tutor variable into the grouping variable. There we go. And then you have the option to calculate the confidence interval. So you can just click the location parameter, 95% confidence, like we did yesterday. And we can also check the descriptives box, which will give us our descriptive statistics and our means and our standard deviation. So let's make sure that for this example, we have it set up as a two-tailed test, and we don't need to make any changes beyond that under the alternative hypothesis heading. Again, if you were going to conduct, like we did yesterday, a one-tailed test, then you would need to update the direction under the alternative hypothesis. So we're going to check our JASP output against the screenshot here on page 12. So let's take a look. We have student t-test, and we have our independent samples t-test results. So the t-value 2.115, degrees of freedom 31, p-value 0.043, the mean difference 5.478, the SE difference 2.589, lower bound of confidence interval 0.197, upper bound 10.759, and let's look at our descriptives. So when we separate the different tutors, again, Anastasia, n equals 15, her mean grades for her student section was 7.53 with a standard deviation of 8.99, with the SE of 2.324, and looks good. And then Bernadette's section was n equals 18. The mean for her students, the grade was lower. It was 69.06 with a standard deviation of 5.775, the SE value of 1.361. So our output is accurate. And again, this is the, we're not using SPSS. We're just using the basic JASP software. And this output is for two independent means. We conducted the two independent means t-test comparing the average scores in Anastasia versus Bernadette's course tutoring sections. So let's go ahead and review the next section here. So the output, again, in figure 9.8, it looks very familiar. First, it tells you what test was run, as we can see by the heading. In case you may have selected the wrong test, you can change it. And it tells you the name of your dependent variables, and it also reports your test results, just like the last time. The test results consisted of the t-statistic, degrees of freedom, p-value, and because we requested a confidence interval, we also see that with our results. The second table, again, we clicked descriptive. So we have the table of descriptive statistics, which is pretty handy when we go to write up our results, because commonly we're expected to report sample size, mean, and standard deviation. So it is really helpful that JASP can calculate this for our for 33 different values instead of us having to do that all by hand. It is pretty important, again, to be clear on what this confidence interval is referring to. So it is a confidence interval for the difference between the two group averages or two group means. So again, in our example, with this data set, the Dr. Harpo data set, we had Anastasia, that tutor, and her students, they had an average grade of 74.533 points. And we compared that, we split the grouping variable by tutor and compared it to Bernadette's students, which had the average grade of 69.056 points. So the difference between the two sample means is the 5.478 points, which we see in the top section. The mean difference was 5.478. But of course, the difference between population means, it might be larger or smaller than this due to random sampling variation. But in this case, we are actually 95% confident that the difference between the two population means is between 0.197 and 10.76 points. In any case, the difference between the two groups, it is just barely statistically significant, as our p-value is 0.043. So we could write up our text like this. The mean grade in Anastasia's class was 74.5 points, n equals 15, SD equals 9.0, whereas the mean in Bernadette's class was 69.1 points, n equals 18, SD equals 5.8. A student's independent samples t-test showed us that this 5.4 point difference was statistically significant, which suggests that a genuine difference in learning outcomes has occurred. T31 equals 2.11, P equals 0.043, 95% CI 0.2, 10.8. So notice that we have included the confidence interval in the statistics block, and people, don't always do this, but at a bare minimum, you would be expected to see the t-statistic, degrees of freedom, and the p-value. So at a bare minimum, your results should say T31 equals 2.1, P equals 0.043. If statisticians had their way, everyone would also report the confidence interval and probably the effect size measure as well, because they are very useful to know. Real life doesn't always work that way with the obsessive compulsive preferences of statisticians, but you should be able to, essentially from the data, make a judgment based on whether you think it will help your readers and your audience, and especially if you're writing a scientific paper, the editorial standard for the journal would require you to provide more data instead of less. Again, some journals would expect you to report effect size, but not all do. And within some scientific communities, it is standard practice to report confidence intervals. Again, in others, it is not. So you will have to figure out what your audience expects from your published results and do that. And just for the sake of clarity, if you're, taking any type of statistics class, the default position will typically be, it's usually worth including the confidence interval. And definitely it is suggested to include the measure of effect size. The next section is something that is important to review, and it's about the positive and the negative t-values that you may experience. So again, a lot of students will commonly worry if they start running like their first t-test and they end up with negative values for the t-test statistic. It is common that a lot of introductory students, they don't quite know how to interpret the negative values. But in fact, it's actually not at all uncommon for two people who are working independently to end up with results that are pretty much identical, except that maybe the one person has a negative t-value and the other is getting the positive t-values. So assuming that you're running a two-sided test and the p-value will then be identical. If on closer inspection the students then notice that like a confidence interval happens to have an opposite sign, it is perfectly okay. Whenever this happens, what you'll pretty much find is that the two versions of the results, they actually arise from just slightly different ways of running the t-test. So what's happening here is pretty simple. The t-statistic that was calculated is always of this form. So t equals mean 1 minus mean 2 over the standard error, or SE. So if the mean 1 happens to be larger than the mean 2, the test statistic will obviously be positive. Whereas if the mean 2 is larger, then if the mean 2 is larger, then your t-statistic would obviously be negative. Similarly, the confidence interval that this statistical software reports is the confidence interval for the difference of mean 1 minus mean 2, which will be the reverse of what you'd get if you were calculating the confidence interval for the difference. So if it was mean 2 minus mean 1. So that seems pretty straightforward when you think about it, but now consider that our t-test comparing Anastasia's class to Bernadette's class. So which one would we call mean 1 and which one would we call mean 2? It seems pretty arbitrary. However, you really do need to designate one of them as mean 1 and the other as mean 2. So not surprisingly, the way that this software handles this is also pretty arbitrary. In earlier versions of this course material, it was used, to try to, we did try to explain it, but then it kind of, again, became pretty insignificant because it's really, it's just a matter of absolute value. So if we get a significant t-test result and then we want to figure out which mean is the larger one, we typically won't try to go and figure it out by looking at our t-statistic. That would be pretty foolish. So it's actually easier just to look at the group means, since our output actually will show them. So the most important thing is this, because it really doesn't matter, what the JASP output will show. we basically have to try to report the t-statistic in such a way that the numbers will just match up with our text so that they are, supporting each other. So suppose that what we want to write in the report is that Anastasia's class had a higher grade than was reported in Bernadette's class. So the phrasing here would imply that Anastasia's group is first, so it makes sense to report the t-statistic as if Anastasia's class corresponded to group 1. And so if we were to write it that way, we would say Anastasia's class had higher grades than Bernadette's class. T31 equals 2.11, P equals 0.043. And we could also write it this way. We could say Bernadette's class had lower grades than Anastasia's class, and the stats would be exactly the same. T31 equals minus 2.11, P equals 0.043. So because we're talking about one group having lower scores in the second scenario, it is basically more sensible to use the negative form of the t-statistic. It just would make sense and it would read more cleanly. One last thing, we want to note that you can't do this for other types of test statistics. It only works with the t-test. So it wouldn't be meaningful when you're doing like a chi-square test or an f-test, and that is the last point that we're going to make for the student t-test when we're looking at comparing two independent means. In our next section, we're going to look at the Welch t-test. And again, we're going to be looking at the two independent means t-test as the Welch t-test this time.